Here we are looking at rational expressions and functions 4.8, REF 4.8. So first thing we want to look at are for horizontal asymptotes. And that we just look at the highest degree. So we've got 2 on the top, 2 on the bottom. When they're the same, we look at the coefficients. So 1 over negative 1, which would become just negative 1. So down here at negative 1 is our horizontal asymptote. Okay, that's the first thing we check. Second is to factor to see what we can get here. So on the bottom, essentially what we want to do is factor out a negative 1, which would give us a positive x squared, negative 2x, negative 3. Okay, so let's see the top. Factors of 4 that would equal negative 5. Well, that would be negative 1 and negative 4. Multiplied would be positive 4. Added would be negative 5. So x minus 1 times x minus 4 here. Now on the bottom, factors of negative 3 that would equal negative 2. Well, negative 3 and positive 1. So x minus 3, x plus 1. Okay. Then we look to see if anything eliminates. So, because nothing eliminates, there's no holes. So then we take the top two, set them equal to 0. That's going to give us our x intercepts. So x minus 1 equals 0, x minus 4 equals 0. So we're basically going to have to add them. So we get x equals 1 and 4. So 1 and at 4 we have x intercepts. Then we take the bottom, basically getting rid of that, set them equal to 0 for our vertical asymptotes. So x minus 3 equals 0, x plus 1 equals 0. So add 3, so we get x equals 3. Subtract 1, so we get x equals negative 1. So at 3, x equals positive 3, we have an asymptote. And at x equals negative 1, we have an asymptote. Okay, now thinking of this, you have to remember that when we have more than one vertical asymptote, this in-between spot, we don't really think of it as having a horizontal asymptote. Okay, so then being the parent function looks like this, right? That's the kind of model we take. So we start here on the left, sweep down, and then just like in those old arcade video games, you go off the screen and you pop up here. We're going to come down until we get to that X intercept and then jump over to the other side. Come down, go off the screen, bring it back down, hit our X intercept, and shoot off. And so it looks like that. Alright, now number 2. This one should be fairly simple. First check the degree, 1 and 1, so coefficients 1 over 1, so horizontal asymptote is y equals 1. Draw my asymptote. Okay. Now nothing can cancel, so I know there's no holes. So to find the x-intercept, we take the top, set it equal to 0, solve for x. Hopefully you're noticing it's basically just the opposite. So at positive 2, we have an x-intercept. Then our vertical asymptote, we take the bottom one, set it equal to 0, solve, get the opposite. So at x equals 1. So there's my vertical asymptote. So then I graph it, knowing that this side is going to have that x-intercept, so it's going to go like that, making me jump over to this side for the other piece. Now it looks like this. Alright, let's take a look at one more. So now we've got, think of this as 3x to the 0 power, so 2 is bigger than 0. Bottom bigger than the top, that means our horizontal asymptote is the x-axis. Or we could write that y equals 0. So we draw it right there. Okay, now the top doesn't have an x, so I know that we don't have any x-intercepts, and nothing can be eliminated. Sorry about that, eliminated. not feeling the best today, so there's no holes. So we just need to find our vertical asymptote. To do that, we need to factor. So we'd have factors of -2 that add up to be 1. Well, probably an x minus 1, an x plus 2. So we take those two bottoms, x minus 1, set them equal to 0, and those are going to give us our vertical asymptotes. So we get at +1 and at -2. Okay. Now normally it'll look something like this, right? And we'll have to connect them. But we don't have an X Intercept, so it's going to look slightly different. Okay. So start on the right side. This right side is usually up here, right? Let's actually make it a different color. Okay, that's pretty normal. Then we're going off screen, so we come up here. But because we don't have an X Intercept, we're actually going to jump back down. What that does is causes us to come up here and shoot it across like that. Okay, so kind of a different look. That's why it's a good idea to have a graphing calculator to double check your shape, make sure you're getting things right. Alright, enough of the graphing. Let's talk about solving rational functions. Okay, so remember the trick with solving rational functions. There's, I guess, two things. First thing is you got to remember, no matter what answers you get, you got to double check them to make sure they don't cause any of the denominators to be 0. Because remember, that's undefined. It doesn't work. Okay. The other thing you want to do is figure out how can we get rid of these fractions because we don't like them. Okay. So think of it this way. How would I get rid of that 5n? Well, I'd multiply by 5n. Okay. In an equation, if I multiply by one number, I have to multiply every piece by that number, right? So, would multiplying by 5n get rid of everything? Yeah, it would, wouldn't it? Because if I multiply this by 5n, the n's would cancel. I'd still have a 5, and I'd get 5n plus 30 for that left side. Okay. And then on the other two, they work out even better, don't they? Because same on the top and bottom, same on top and bottom. But because I multiplied every single piece by the same one, that's why I can do it. That's what allows me to get away with doing that. Okay? Now this negative also kind of applies to the whole thing. Okay? So I would actually just distribute that negative and make it minus n minus 3. Then we just simplify. So n minus n gets rid of those n's. 6 minus 3 gives us 3. So 5n plus 30 equals 3. Subtract by 30. And we get 5n equals negative 27. So divide by 5. And we get n equals negative 27/5. Okay, so now we've only got one answer, so if we look at these bottoms, if I multiply 5 by that, it's going to be negative 27. So none of them are going to equal 0, so that's our answer. Okay, so that's one way to do it. Another way to do it would be to think of these as a system of equations, a system. If I graphed this side and then this whole side, if I graph those together and find where they intersect, that's another way that you can get to that same answer. So there's more than one way to do it. So let's look at number 5 now. Okay, so we've got 2n squared, n squared, n. So what would be the common, I guess, denominator you could say in that? Well, we've got to multiply by 2 to get rid of that 2. Okay. We've also got to multiply by n to get rid of that n, and multiply by another n to get rid of those two n's. So basically 2n squared will get rid of everything. Now, will it completely get rid of itself? No. Because if I multiply this side by 2 times n, which is 2n squared, and this one by 2n squared, and this one by 2n squared, On the right side, I only get rid of one n, so I'm left with 2n, which is alright, because then I just distribute. So minus 1 times 2n is 2n. The middle one gets eliminated completely, which we like. The left side only gets rid of the n squared, so I distribute the 2, and I get 2n minus 4. Then I add 2n to both sides, giving us 4n minus 4 equals 1. Add 4, and I get 4n equals 5. Divide by 4, we get n equals 5/4. Okay, which is another one that won't make any of those equal to 0, because if I square it and times it by 2, it's not going to get to 0. Okay, so there's our answer. Once again, you could just graph the left side and the right side and find the x value of where they intersect, and that would get it for you too. And that really only makes sense if you're using some sort of graphing calculator, because if not, then it's going to be tougher to make it work that way. Okay, so let's take a look at number 6. So we've got 6x and 3x, and think of that as 1. So if I multiply by 6x, will I get rid of the 3x? Yeah, because 6x is like 3 times 2 times x. So you'd have a 2 left over. So I times every piece, even the 1, by 6x. That's easy because it becomes 6x minus, those cancel completely, giving me 1, equals, now the 6 is really 2 times 3, so 3x gets eliminated. I keep the 2, multiply it by the 4. And we add 1 to both sides, and I get 6x equals 9. Divide by 6, and we get x equals 9/6, which is 3/2 or 1.5. Okay, which then if I look at the bottom here, to double check, 3 times 1.5 isn't going to get to 0. 6 times 1.5 isn't going to get to 0. So, there's my answer. Alright, so hopefully you're getting the hang of what we're doing here, and you should be trying these on your own. Now, r minus 7. Okay, and that doesn't have a denominator, so it can be multiplied by whatever. So I'm going to multiply by r minus 7. It's alright to multiply by a binomial. You can multiply in equations by anything. Okay? So 1 times r minus 7, I'll write it out a little more. R minus 6 over r minus 7. As long as we're multiplying each piece by the same one, that's why it works. Okay, that's why I'm not having to multiply by this, because I'm multiplying every piece of my equation by the same number. Just like when we dealt with systems as a freshman in Math 1, you could double an equation or triple it to get it to work out to what you needed it to be, because you multiplied every piece by that same number. So those cancel, that becomes r minus 7. We're left with r minus 6 plus 2r plus 8. So let's combine like terms. R and 2r would give me 3r. Negative 6 and 8 would give me positive 2. R minus 7. So we could subtract r from both sides. So negative 7 equals 2r plus 2. Subtract 2. We get negative 9 equals 2r. Divide by 2. You get negative 9/2, or negative 4.5, or even negative 4.5, same thing. Okay, so all of those are the same answer for r. Now if we go back up there, if I subtract 7, will they make it 0? No, it won't. So they work. So those are our answer in its different forms. Alright, let's finish this out. So I'm going to need to multiply by 4k. That'll get rid of that k. So each one of these terms I have to multiply by. So the k's cancel, 4 distributes, 8k plus 16, 4k, subtract, those cancels, and we get 1. So I add 4k to both sides, we get 12k, subtract 16, get negative 15 equals 12k, divide by 12, we get negative 5/4 equals k. or negative 1 1/4, or negative 1.25. Okay, once again, those won't make anything 0, so there's my answer. Okay, number 9. We'll need some space, won't we, for this one? So, I need to multiply by the x squared plus x. But that won't get rid of this, right? That won't eliminate that because that's a package deal. So what I end up having to do is say, okay, take this one and multiply them together. So x times x squared plus x. That's what I'm going to multiply to each one of these. Because if I make them factors like that, then I can get rid of the piece that I need to. I will have some left over, but that's alright. So I'm timesing by that whole thing. Okay, what that'll do is those x's will cancel. 1 will be times that whole piece. So on the right side we get x squared plus x. The x squared plus x cancels, x times by 1, so I get x. The x squareds cancel, then I multiply that to get 7x squared plus 28x as I distribute. Then we combine like terms. Subtract an x, those cancel. Subtract an x squared, 7 minus 1, 6x squared plus 28x equals 0, because I used up everything on the right side. So now we factor. Can 6 go into 28? It can't, but we can pull out an x. So we get x equals 6x plus 28 equals 0. Then I split them up. X equals 0, so I've got one answer. 6x plus 28 equals 0. Subtract 28. I get 6x equals negative 28 divided by 6. We get x equals negative 28 over 6, which would be what? 4 2/3? Negative 4 2/3. Okay, so I have a possibility of two answers, so let's go back and check them. If I plug in zeros for x's, I'm going to end up with 0 on the bottom, right? That's an extraneous answer. That won't work. If I do that one, it'll be fine. So we're good there. So that's my only answer. This one eliminated. Alright, let's keep on moving. So, now this is where it gets a bit crazy. Okay? So, because we've got p squared plus 3p and p plus 3. But I don't necessarily want to set it up like this, right? For my common denominator. Which is kind of what we're looking at, essentially getting. But you can think of it, or I guess look and see if there's a piece you can simplify. Well, p squared plus 3p, they share a p, right? If I pulled that out, I'd end up with p plus 3. So in all actuality, if we multiply everything by that p squared plus 3p, we end up eliminating the bottoms. Okay? So we'd multiply this one by the p squared plus 3p. We'd multiply this one, and I'm going to write it in that factored form. And then we multiply this by the p squared plus 3p. So those ones would cancel. This one would multiply by 1, giving us p squared plus 3p, plus those two canceled, so we're left with 8, equals the p plus 3's would cancel, so I'd have p times p, or p squared, minus p times 1, which would be p. Then we can simplify. Subtract p squared from both sides. That would cancel those out, which is what we like to see. So we'd have 3p plus 8 equals negative p. Subtract 3p. And we get negative 4p equals 8. Divide by negative 4. And we get negative 2 equals p. Okay? And there's our answer. Because if we plug it in for either of those, we're not going to end up at 0, so it's our real correct answer. Alright, now let's take a look at 11. Okay, now this one's even more crazy, right? So let's simplify these first. So I've got 2 times p plus 6. I've got 2. And this one we'd simplify would be p factors of negative 18 that add up to 3. Let's see. 3 and 6. And if the 3 is negative, so the 6 is positive, that would work, right? So our biggest question here is, if I multiply everything by this, will I get rid of this, and will I get rid of this? Well, the factored forms share the p plus 6's. So I'd be able to get rid of the p plus 6's, right? With the multiplying. I wouldn't be able to get rid of the 2's. So I'm going to have to basically multiply everything by 2 times p plus 6, p minus 3. Okay? So I multiply that by every single piece here. So all 3 of these fractions are being multiplied by it. And what happens is, that cancels out with that whole piece, so I'm left with 2 times, on the top, 3, so we have 6, plus the 2's cancel out, so I'm left with that whole piece, which I could write as a factored form. I know it's the same as that, so I'm going to actually write it out instead, because it was 1 times that, so it remains the same, equals, now the 2's canceled here, the p's plus 6's canceled here, so we're left with p minus 3 and p minus 3. So we've got this going on, right? P minus 3 squared. So factor that, or not factor, multiply, p squared minus 3p minus 3p plus 9, or p squared minus 6p when we combine like terms, equals 6 plus p, well I guess we can simplify that a little bit too, right? Positive 6 minus 18 would give us p squared plus 3p minus 12. Subtract p squared from both sides. Those cancel. I could add 12 to both sides. And I could add 6p to both sides. So 9 and 12 would give us 21. 3 and 6 would give us 9p. Divide by 9. And we get p equals, 9 goes into 21 twice. And there's 3 ninths, or 1/3, so 2 1/3. So 2.3 basically. Which I could plug into there. 2 1/3, that definitely won't be 0, won't be 0. 2 1/3, 2 1/3, that won't be 0 either. Alright, so there we go. Quite a bit of work, isn't it? Alright, now simplifying each expression, kind of the same way of what we just did, right? That we would multiply to get common denominators, do it on the top and on the bottom, because we don't have that equal sign, so we can't do it the way we were doing the other one, and just get rid of them. Okay? Which basically this would do the same thing anyway. So 2x times 5x would be 10x squared. 2x times 3 would be 6x. Think of that as a negative 5x. Plus negative 5x times x, negative 5x squared. Plus 20x. All of that over 5x plus 3 times x minus 4. Combine like terms. That would give us 5x squared plus 26x over our denominator, which we can't simplify any of this, so we'd call it good right here. And there's our answer. I mean, I could pull an x out, but we're not going to be left with anything that would eliminate any of these, so it's not worth trying. Okay. Same with this one, times this side by 3p minus 3, times this side by 4. We get 4 times 3p minus 3 under 3p times 4 would be 12p squared minus 12p plus 24, which we can pull out of 12, right? 12 times p squared minus p plus 2 over 4 times 3p minus 3. Can't cancel those at all. I can't factor that without coming up with an imaginary number or something. 12, however, is 3 times 4, so the 4's can cancel. So we have 3 times p squared minus p plus 2 over 3p minus 3. And there would be our answer on that one. Alright, let's take a look at these last ones now. Okay, same process here. Times this side by b minus 2. Times this side by 3b plus 2. Get our common denominator of 3b plus 2 times b minus 2, 2b times b, 2b squared, 2b times 2, negative 2, negative 4b, plus 4b times b, 12b squared, plus 4 times 2, 8b. Then simplify, 14b squared minus, plus 4b over 3b plus 2 and b minus 2, which I could pull out a 4 and a b, but it's not going to leave me with what I want, so I just leave it that way. Okay, now the last one, same thing, times by n minus 2, times the left by n minus 4. That becomes our denominator, n minus 4 times n minus 2 over, or under, that would be 6n squared minus 24n. Think of that as plus a negative 4n. So it would be negative 4n squared plus 8n. Combine like terms, so that would be 2n squared minus 24 and 8 would give us 16n over n minus 4 times n minus 2. Now this top looks like maybe it could work if I pulled out a 2n and end up with n minus 8. So nope, not quite. So I could leave the top like this, or just leave it all like that and call it good, which is what I'm prone to do here. So there we go, and we're done.